Greetings of the day. In our last lecture, we have already discussed different types of power quality problems which come under the category of uh, voltage and current variations. If you remember, about 8 types of power quality problems were discussed: voltage magnitude variation, voltage frequency variation, voltage fluctuations, voltage flicker, current magnitude variation, current phase variation, three-phase unbalance, and in previous lecture we discussed voltage harmonics, causes of voltage harmonics. If you remember, I told you that there are predominantly 4 causes of voltage harmonics or voltage distortions, like harmonics, interharmonics, voltage notching, and DC bias in the loads. We also discussed about the bad effects of harmonics on the system, both consumers as well as utility. Now, in today's lecture, we are going to discuss the second type of power quality problem, second category of power quality problem. That is, second one is, if you remember, events. First one was voltage and current variations, and under the under that category we have discussed various types of 8 types of power quality problems. The second category is events. First of all, what is an event? An event is a phenomenon, or we can say an event is a phenomenon which only occurs every once in a while. Like, it will occur, say, this time, and it may not occur periodically, repeatedly. So I repeat, event is a phenomenon which only occurs every once in a while. So let me write it, it is better. Event is a phenomenon which only occurs every once in a while. Once in a while. So this is the definition of an event. The best example of event is interruption. Suppose there is disruption of power, there is blackout, the power goes off. That's called interruption. The power is interrupted. So as you know, interruptions are not periodic in nature. They do not occur periodically. They occur once in a while. There may be an interruption of the service, an interruption of the supply now, and it may not occur periodically. Next interruption, we don't know when it occurs. It may occur tomorrow, it may occur after 1 month, it may occur after 15 days, it may occur after 2 months. So best example of an event is this interruption. There are other types of interruption, other examples of events we will discuss in due course of time. Now, what these events do, they result in tripping of the motors, tripping of the processes, stoppage of the processes, loss of production, loss of revenue, and they also result in danger to power system protection equipments. Okay, now what are the various types of events? Events are of following types. Number 1, transients. Transient is an example of an event because transient occurs only once in a while. Second example of event is first is transients, second is interruption or interruptions. Third example of event is under voltage under voltage and voltage sag. And fourth type of event is over voltage and voltage swell. So these are predominantly 4 types of events which are encountered in power systems and which affect the operation of equipments, especially the sensitive equipments, they result in tripping of the equipments, they result in disruption of the industrial processes, and hence they result in wastage of raw materials, they result in loss of production, loss of deliveries, loss of supplies, and loss of revenue. We will discuss them one by one. Now, the first type of event is transients. Let us start with transients. I will write here first type of event, transients. If you remember, in one of the earlier classes, I have already briefly discussed about transients, and I told you that these transients are of two types, impulsive transient and oscillatory transient. Impulsive transient and oscillatory transit. oscillatory transient. These are two types of transients. Let us discuss them one by one. First of all, we will discuss impulsive transient. Impulsive transient. How do you define impulsive transient, and what actually is an impulsive transient? Well, an impulsive transient is a sudden non-power frequency unipolar change. All right, impulsive transient is a sudden change, sudden non-power frequency change. Non-power frequency means it is not 50 hertz. This change does not take place at 50 hertz, and it is a unipolar change. Unipolar change means, a transient may be either positive transient or it may be negative transient. Okay, so it's that's called unipolar change. So for example, there may be a sudden if you take the impulsive transient in voltage, the voltage may suddenly rise, and it will be non-power frequency rise in the voltage. It will not be 50 hertz rise in the voltage, and it will be unipolar increase in the voltage. Okay, now the question is, what are it's a sudden non-power frequency unipolar change. Amplitude, it is characterized by, I'll write here, characterized by high amplitude, fast rise time, fast fall time or decay time, fast rise, fast decay, and high energy density. So please try to understand what an impulsive transit is. It's a sudden change and a unipolar non-power frequency change, and it is characterized by high amplitude, fast rise, fast decay, and high energy density. Example of a transient, an impulsive transient may be like this. Let us suppose this is voltage waveform V, 0, pi, 2 pi. Okay, so there may be impulsive transient, say somewhere here, a very large increase in voltage. Suddenly the voltage at this point, very close to 90 degrees or very close to peak of the voltage, there is a sudden rise in the voltage. So it's a sudden change. Sudden change means sudden rise in the voltage, and it's a unipolar change. It's a positive increase in the voltage. It may occur here. Right now I am showing it near the peak. It may occur anywhere in the waveform. It may be a positive impulse, or it may occur in the negative half cycle of voltage also. Okay, and then it is characterized by high amplitude. If this voltage has a peak of 325 volts, this voltage may have an amplitude of thousands of volts. Fast rise time, you can see it rises very quickly. Fast decay time. It decays also very quickly, and it has a very high energy density. This is what you mean by impulsive transient. Now, an impulsive transient is also called voltage surge or voltage spike. It is also called voltage surge or voltage spike. These are the other names given to impulsive transient in literature: voltage surge or voltage spike. And what are the causes of these impulsive transients? Causes are capacitor switching. Suddenly you may switch a capacitor bank or a capacitor, that may result in impulsive transient. And faults, circuit breaker out of adjustment. If circuit breaker is out of adjustment, that will also result in certain changes in the voltage, that is impulsive transient. Circuit breaker out of adjustment. And mainly the main cause of impulsive transient is mainly because of lightning strike. Lightning strike. Lightning strike is the main cause of impulsive transient. Okay, now let me give you a diagram of a distribution system. This is a distribution system. This is source here. It may be a distribution transformer. Then you have this is feeder 1. Let us suppose this is feeder 1, and this is bus 1. And then you have another feeder. Let us call this feeder 2, and this is bus 2. You have two loads connected at the two feeders, at the two buses. This is load connected here at this bus, and you may have one more load connected to this bus. So this bus also feeds a load. Now at bus number 1, you may have a capacitor also connected. Maybe for power factor correction, you have a capacitor C also connected there. It is connected through the switch. Now let us suppose a lightning strikes. There is a lightning strike very close to this transformer, or it may be a generator, very close to the source. There is a lightning strike. Because of this lightning strike, what happens is that the magnitude of the voltage increases. So it is something I can show you graphically like this. You have to understand it graphically. This is time axis. Let us suppose this time is 0.02 second. Let us suppose at 0.02 second, time is in, of course, seconds, lightning strikes. And this is voltage impulse because of lightning strike, voltage impulse. That is lightning voltage in volts. So this is 5 per unit. Let us suppose it is not in volts, it is in per units, not in volts, it is per unit. This is, and it has an amplitude of 10 per unit. So now we can see this is the lightning strike. This is the characteristic of lightning strike. Let us suppose it comes at 0.02 second, and it lasts from 0.02 second to 0.021 second, just for 0.01 second. So at this point P, lightning has struck. What is the amplitude of the lightning voltage because of lightning? Okay, this is the characteristic of a lightning strike. It has a very, very high amplitude, 10 per unit, and then it decays, and finally at 0.021 second it decays completely. Now as soon as this high amplitude lightning strikes at this point, which is very close to the source, it results in change in the feeder current slightly. This feeder current 1 may change slightly. Let me show you feeder current. This is again time, and the time is in seconds, and this is this axis, y-axis is feeder 1 current. Let me show you feeder 1 current. Okay, again this feeder 1 current is in per unit. Now this is 0.5 per unit, minus 0.5 per unit, and so on. And now see, let us suppose the maximum amplitude of current is 0.5 per unit. This is the end of one cycle. At 50 Hertz frequency, A cycle is of, what is the time period of cycle? 20 milliseconds. And 20 milliseconds means 0.02 second. And at t equal to 0.02 seconds, so this time is 0.02 second, lightning strike is there. And as soon as lightning strike is there, the current magnitude will slightly change. It will slightly increase, not much. And then it comes back to normal value, steady state value. But there is a slight increase in this current from, say, maybe 0.5 per unit to, say, 0.6 or 0.7 per unit. So therefore feeder 1 current changes. Now what happens to the voltage at bus 1? It is interesting to see the voltage waveform. What happens to the voltage at bus 1? Let us try to see what happens to the voltage at bus 1. Again, this is time axis in seconds, and x-axis time in seconds, and y-axis is, say, bus 1 voltage. Bus 1 voltage. And this bus 1 voltage is in per unit. Now, let us suppose this is 2, 4, 6, 8, similarly -2, -4, and so on. Let us suppose the normal value of voltage is 2 per unit. Bus voltage, bus 1 voltage has a normal value of 2. Now this is time t equal to 0.02 second, and at t equal to 0.02 second, there is a lightning strike. As soon as there is a lightning strike here, what will happen? This lightning strike will result in voltage impulse or impulsive transient. This is the impulsive transient. And what is it has a very fast rise time and very fast decay time. And what is the amplitude of this impulsive voltage transit? It is between 6 and 8 per unit. That is, it's around 7 per unit. Normal amplitude of the voltage is 2 per unit, but as soon as this lightning strikes here at t equal to 0.02 second, there is a voltage impulse, or there is an impulsive transient whose amplitude goes from 2 per unit to around 7 per unit. So it's a huge increase in the voltage, and then it rises quickly and it decays also quickly, and then voltage comes back to its normal value. This is bus 1 voltage. Similarly, it will have an effect on bus 2 voltage. Bus 2 voltage will also see a transient, but it will see a transient which is less than this transient. Let me draw bus 2 voltage here. Time axis is again in seconds, that is x-axis, and y-axis is, let me write here, bus 2 voltage, and this bus 2 voltage is also in per unit. Now this is 2 per unit, this is 4 per unit, this is 6 per unit, this is 8 per unit. Similarly, -2, -4. The steady state value of bus voltage is 2 per unit, as in this case. And then as soon as this lightning strikes, there is an impulsive voltage or voltage transient, impulsive voltage transient on bus 2 also. It rises very quickly, falls very quickly, and then voltage comes back to its normal steady state value. Now, what is the difference between impulsive transient at bus 1 and impulsive transient at bus 2? The impulsive transient at bus 1 has an amplitude of 7 per unit, whereas impulsive transient at bus 2 has an amplitude of only 5 per unit. So therefore, the effect of this lightning strike, as you go away from this point, it has less and less effect. If you would have another bus, say bus 3, at bus 3 also you would have found impulsive transient, but that impulsive transient would its amplitude would have been even less than this. So therefore, as soon as lightning strike of this characteristic is there on the feeder, it results in impulsive transient on bus 1 as well as impulsive transient at bus 2, with the assumption that capacitor is not connected. Capacitor, which is connected for power factor improvement, let us assume capacitor is not connected. So this is case A, which we were discussing. That is, C is open. I mean, capacitor is not connected. What will happen if capacitor is connected? Let us see that case also, case B. Second case we will now consider. I will write here case B. Capacitor is connected. Let us suppose capacitor is connected through this switch. Now when capacitor is connected and we assume that now lightning strike has also occurred at this point in presence of capacitor, what will be the nature of impulsive transient? Will it be same as that without capacitor, or its characteristics will change? You have to find out that. Now for that purpose, we have to first of all see the feeder currents. This is time axis in seconds. Let us write here feeder 1 current, which is in per unit, 0 to 4 per unit, minus 2, minus 4 per unit. This is 1 per unit. Let us suppose feeder current is 1 per unit. Up to t equal to 0.02 second, it's normal current around 1 per unit. And then at t equal to 0.02 second, there is a lightning strike here. Now, but capacitor is switched on, it is connected into the system. Because of this capacitor, there will be impulsive transient of this type. I mean, first of all, there will be changes in the current. Current will rise above, so it will have this type of characteristic. So this will be the nature of feeder 1 current. So feeder 1 current will oscillate. It will see the oscillations. It will see rise in the amplitude and oscillations. And then these oscillations will die out and current will come back to its steady state value. This is feeder 1 current. What is its effect on the bus 1 voltage? Let us try to see bus 1 voltage. This is time axis in seconds, and this is bus 1 voltage in volts. Let us try to see bus 1 voltage. This is 0, this is 2, this is 4 per unit, minus 2 per unit, minus 4 per unit. Let us suppose bus voltage, when there is no lightning strike, it is 2 per unit, its amplitude is 2 per unit. At t equal to 0.02 second, lightning strike is there. So what will happen to the voltage? There will be impulsive voltage. In the previous case, you have seen that impulsive voltage was of this type, but now it will not be of that type. It will be of this type. It will be of this type. It will be high frequency. I mean, there will be some sort of oscillations. And the amplitude of impulsive voltage will go as high as 4 per unit. Whereas in the previous case, without capacitor, you have seen that the amplitude of impulsive transient goes as high as 7 per unit. So the good news is that amplitude of impulsive transient is not 7 per unit, it's only 4 per unit, but it remains there for longer period because it goes high, low, then again high, low, and till it decays. So similarly, feeder 2 current will have less effect, and bus 2 voltage will also see the impulsive transient, but the amplitude of impulsive transient will be even less than this. Okay, so this is the impulsive transient in presence of capacitance. Without capacitance also we have seen, and in presence of capacitance also we have seen. Okay, that was about first type of transient, that is impulsive transient. Now, the impulsive transients generally do not travel much beyond their point of origin, and that's a good point. That is, they don't propagate along the line. But impulsive transients may give rise to another type of transient, which is called oscillatory transient. So let me write here oscillatory transient. Now this oscillatory transient is also sudden change, sudden non-power frequency change, just like impulsive transient. Oscillatory transient is sudden change, non-power frequency change, and it is bipolar in nature. and it gives rise to what we call as ringing. Ringing means it is not a change like this. It's not. It results in frequent oscillations. Results in oscillations, and that oscillations give rise to what we call as ringing. Okay. Now, before we draw the waveforms and I try to show you the oscillatory transient, it is better that we understand the causes of oscillatory transient. What are the causes of oscillatory transients? Capacitor switching, sudden capacitor switching is one of the causes of oscillatory transients, and load response, load or system response to impulsive transient. I mean, there is an impulsive transient, and how your load responds to that impulsive transient, how the system responds to that impulsive transient. Whenever there is an impulsive transient, the load response or the system response is such that this impulsive transient gives rise to what we call as oscillatory transients. It gives rise to oscillatory transients, which I have written here. Now, these oscillatory transients are decaying in nature, and these oscillatory transients I can show you here. This is time axis and this is voltage. Voltage may be in per unit. They are of oscillatory transients, maybe of this type. So let me first of all draw. I mean, there are high frequency oscillations in each. High frequency oscillation here, high frequency oscillations here. Whenever impulsive transient is there, it results in oscillatory transients, and these oscillatory transients acquire high amplitude, decrease, increase, decrease. So it's like this, high frequency oscillations. So this is one high frequency oscillation, followed by another wave of high frequency oscillations but of lower amplitude, followed by another series of high frequency oscillations but of even lower amplitude, finally till these oscillatory transients decay completely. So this is the nature of oscillatory transients. Now, these oscillatory transients have frequencies. If the frequency is greater than 500 kilohertz, if the frequency of these transients is greater than 5 kilohertz, they are called high frequency transients. Of course, oscillatory transients. They are categorized as high frequency transients. If the frequency is between 5 kilohertz to 500 kilohertz, they are called medium frequency transients. Medium frequency transients. And if the frequency of transients is less than 5 kilohertz, they are called low frequency transients. Low frequency transients. So this is about oscillatory transients. The problem with oscillatory transients is that these oscillatory transients may travel along the line, and they may impress very high voltage across line insulators, and they may cause puncture or damage of line insulators. So this was about first type of power quality problem, which comes under the category of events. Now, why this type of power quality problem, that's transients, whether it is impulsive transient or oscillatory transient, why it comes under the category of events? Because these oscillatory transients or impulsive transients occur only once in a while. You know, your line or your feeder does not receive lightning strike every day. Lightning strike may occur only once in a while, maybe once in 6 months, once in few months. And whenever this lightning strike is there, this lightning strike results in impulsive transients, and these impulsive transients may initiate oscillatory transients. And one best way of arresting the impulsive transients is to use surge arrestor. There is one protective device called surge arrestor. Surge arrestors are used for arresting these transients. So that was about first type of power quality problem, which comes under the category of events, that is transients. And we have classified these transients into two categories: impulsive transients and oscillatory transients. Impulsive transient is a sudden non-power frequency and unipolar change in the voltage, a large increase in the voltage, high rise time, fast decay time, and high energy density. Whereas oscillatory transients are also sudden non-power frequency but bipolar changes. Bipolar means you have seen it's ringing. Ringing means it's like this. It goes positive as well as negative. Okay, so it's not a unipolar transient, it's a bipolar transient. That was about first type of power quality problem under the category of events. The second type of power quality problem under the category of events is interruptions. Now, interruptions have been given different names in the literature. According to IEEE standard 1159, it's called voltage interruption. Voltage interruption. IEEE standard 1159 calls it voltage interruption. You can search the literature, you can Google it, and you will see this IEEE standard 1159 calls this type of power quality problem as voltage interruption. There is another IEEE standard, that is IEEE standard 1250, IEEE standard 1250, that simply calls it interruption. It does not call it voltage interruption, it simply calls it interruption. And there is one more standard, and that is EN 50160 standard. According to this, it's not an IEEE standard, it's IEC standard. And according to IEC standard EN 50160, they call it supply interruptions. Supply interruption. So these are different names given by different standards to interruptions. IEEE standard 1159 calls it voltage interruption. IEEE standard 1250 calls it interruption, or IEC standard EN 50160 calls it supply interruption. Now the question is, what is this interruption? Whether you call it voltage interruption or supply interruption or simply interruption. How do you define this interruption? We can define it that it is a condition in which the voltage at supply terminals is close to zero. So it is a condition in which voltage at supply terminals, is close to zero. Close to zero means less than 1% of declared voltage, less than 1% of declared voltage as per IEC standard, or it means less than 10% of declared voltage as per IEEE standard 1159. Okay, so we say that an interruption has occurred if voltage at supply terminals has become very close to zero. Very close to zero according to IEC standard means less than 1% of the voltage, declared voltage. And according to IEEE standard 1159, if the supply terminal voltage goes less than 10% of declared value, then it is called interruption. So it may go even less than zero, means less than 1% means zero, less than 10% also means zero. It may simply go to zero, or it may go to a value which is less than 1% as per IEC standard, or which is less than 10% as per IEEE standard 1159. Now that is about the definition of interruption. Now actually these interruptions are caused by the faults in the power system or in the distribution system, which cause the operation of protective devices, because whenever a fault like a short circuit or a ground fault is there on the system, the protective relays operate, and when protective relays operate, they trip the circuit breaker trips, and when circuit breaker trips, the faulty part is kept out of the service, and at that time the supply interruption occurs. Now most of the or majority of these faults are on overhead lines. They are overhead lines, and they are temporary in nature. And these faults are caused by situations like tree branch cause these faults, birds, animals. And what type of faults they cause? They cause short circuits or shorts or grounds. For example, let us suppose a tree branch has fallen on a feeder. This is the three-phase feeder, and tree branch has fallen between the two lines. And when this tree branch falls, it causes a short circuit. And it's a temporary fault. What happens to this tree branch? When a short circuit is there, a high current flows, it burns out and it falls down. And as soon as it falls down, the fault is automatically cleared. But in this process, when this short circuit because of tree branch occurs, the protective relay has operated and it has tripped both the lines, and therefore there is supply interruption. Okay. Similarly, a bird may result in short circuit. An animal on the ground may result in the grounding situation or grounding condition, and therefore these tree branch, birds or animals, they cause shorts or grounds, and because of these shorts or grounds, the operation of protective devices is there, and they trip the line, they trip the system, and that causes the interruptions. Now, other causes of interruptions may be other causes. So these are natural causes. Other causes may be maltrip of relay. Maltrip of relay means the relay is tripping without a fault. Because the relay is maltripping, it's not operating properly. There is some problem with the relay. That's called maltrip. Or it may be due to operator intervention. The operator at the substation may close the switch, it may trip the line, and that will result in interruption. Okay. Another category of, or another way of classifying interruptions is between prearranged trip and or prearranged interruption and interruption accidental interruption. Accidentally prearranged means that operator trips the line, there is an interruption, and accidental means the same operator trips the line but accidentally, it's not prearranged. So this is another these are the other ways or other causes of interruption. First, tree branch, birds or animals, these are the natural causes, or there may be maltrip of the relays, maltrip of the protective devices, or operator intervention, or prearranged or accidental interruptions. So these are various types or various causes of interruptions. Now, interruptions are classified differently by IEC and IEEE. According to IEC, International Electrotechnical Commission, they classify interruptions as short interruptions and long interruptions. Short interruptions and long interruptions. Now, according to IEC, an interruption is said to be short interruption if it lasts up to 3 minutes. If the interruption lasts up to 3 minutes, maximum 3 minutes. It may be few seconds or maximum up to 3 minutes. If the interruption lasts up to 3 minutes, it's called short interruption. And a long interruption is that interruption whose duration is greater than 3 minutes. If the duration of interruption is greater than 3 minutes, it's categorized or classified as long interruption. And if the interruption is up to 3 minutes or less than 3 minutes, it is classified as short interruption by IEC. But IEEE, that is the Institute of Electrical and Electronics Engineers, IEEE, they classify interruptions as momentary interruptions, temporary interruptions, and sustained interruptions. This is their classification. So they classify interruptions into 3 groups: momentary interruption, temporary interruption, and sustained interruption. An interruption which lasts from 0.5 cycle to 3 seconds, that is called momentary interruption. See, 1 cycle means 20 milliseconds on 50 hertz, and 0.5 cycle means 10 milliseconds. 10 millisecond means 0.01 second. That means if an interruption lasts from 0.01 second, that is 0.5 cycle, that is 0.01 second to 3 seconds, it is classified as momentary interruption. If an interruption lasts from 3 seconds to 1 minute, it is classified as temporary interruption. And if the duration of interruption is greater than 1 minute, it is classified as sustained interruption. So according to IEC, interruptions are of 2 types: short interruption and long interruption. A short interruption is the interruption which lasts or whose duration is up to 3 minutes, and an interruption is said to be long interruption if its duration is greater than 3 minutes. And according to IEEE, the classification of interruptions is as momentary interruption, an interruption whose duration is 0.5 cycle to 3 seconds, temporary interruptions whose duration is from 3 seconds to 1 minute, and sustained interruption whose duration is greater than 1 minute. So now, whenever there are these interruptions, whether it is a short interruption or long interruption, or whether it is a momentary interruption or temporary interruption or sustained interruption, it results in tripping of the motor drives, adjustable speed drives or variable frequency drives. It results in loss of production and hence loss of revenue. And it's a grave power quality problem. It's a grave power quality issue. So that was about interruptions. Third type of power quality problem is under voltage and voltage sag. Under voltage, under voltage and voltage sag. Now, if the under voltage is of short duration, that is short duration under voltage, is called voltage sag. I will write here short duration under voltage. It's called voltage sag by IEEE. Voltage sag by IEEE, and it is called voltage dip by IEC. Voltage dip by IEC. If you see IEC literature, they call it voltage dip. If you see IEEE literature, they call it voltage sag. So any short duration under voltage or reduced voltage or any short duration voltage, that is called voltage sag by according to IEEE, or voltage dip according to IEC. And long duration under voltage is called under voltage itself. I will write long duration under voltage. It's called under voltage itself. Under voltage. So under voltage is long duration under voltage, and short duration under voltage is called voltage sag or voltage dip. Now, how do you define this voltage dip or voltage sag? A voltage sag is a reduction in the supply voltage magnitude to a value between 90% and 1% of the declared value. So therefore, how do you define voltage dip or voltage sag? It is reduction in supply voltage between 90% and 1% of declared voltage. That is followed by a voltage recovery. Voltage recovery after a short period of time. After a short period of time, and this short period of time means 10 milliseconds to 1 minute. Okay, there is a voltage sag, reduction in the voltage. Reduction in the voltage means आपकी voltage 90% से कम हो जाती है, but it may be as low, it may go as low as 1%. अच्छा, अगर 1% से कम हो गई तो उसको हम interruption कहते हैं according to IEC. This is also IEC definition. लेकिन अगर 90% से कम हो गई वोल्टेज, 90% तक गई या 90% से कम but up to 1%, that comes under the category of voltage sag. But if voltage is even less than 1%, then that is not voltage sag, that is voltage interruption. That's interruption. And followed by a voltage recovery. I mean, it is a temporary sag in the voltage. It is followed by quick recovery after a short period of time. After 10 milliseconds to 1 minute, it recovers again. So it is something like this. Normal voltage is there, normal voltage, and suddenly a fault has come and voltage sag has occurred. Say for 2 cycles, and then it comes back to normal value. So this is the normal value of the voltage, normal amplitude of voltage, and then this is the dip in the voltage. It may be there for 2 cycles, 3 cycles, say maybe 10 milliseconds to 1 minute, and then voltage recovers, comes back to its normal value. Now this is IEC definition. That is, voltage falls between 90% and 1% of declared voltage. But IEEE, according to IEEE, the voltage should fall, if the voltage falls between 90% and 10%, not 1% of declared voltage, then it is voltage sag. Because you have just a few moments back seen that if voltage is below 10% as per IEEE, then that comes under the category of interruption. But if the voltage is 10% or above 10%, I mean, if voltage dips, voltage falls to 90% or below 90% up to 10%, then it is voltage sag. It is not voltage interruption. Okay. Now, what are the causes of this voltage sag? Causes may be large motor starting, as you already know. You are starting a very large induction motor or very large motor, and that causes dip in the voltage. Short circuits, I mean temporary short circuits, which are there for very small period, they also cause dip in the voltage. Single line to ground fault, it will also cause dip in the voltage, maybe dip in voltage of that particular phase or that particular line. Okay. And then voltage on adjacent lines, faults on adjacent lines. Faults on adjacent lines. So these are various causes of voltage sag or voltage dip. Okay. Now these voltage sags, we have already discussed in one of the lectures that these voltage sags are really a cause of concern for all industrial processes. These voltage sags result in tripping of the computers. They result in in hospitals, sensitive loads like hospitals. They result in maloperation of critical equipment, sensitive equipment, like in the operation theaters, various equipments may maloperate. Life support system, ventilators, they maloperate, they misoperate because of these voltage sags. And in hospitals, patient data system may get erased, it may get damaged because of these voltage sags. And in industries like semiconductor manufacturing industry or food processing industry, etc., these voltage sags result in tripping of the motors, tripping of the drives, adjustable speed drives, and hence stopping of the process. And when the process stops, the entire batch of products which is under manufacturing process, that gets damaged or ruined. and hence there is a loss of revenue, there is loss of raw material, loss of time, loss of production, and above all, there is huge loss of revenue. I have told you in one of the early classes that these voltage dips result in loss of revenue in Western countries, in advanced countries, worth millions of dollars every year. Okay, and they have to be taken care of. That is about under voltage and voltage sags. Now, fourth type of power quality problem under this category is over voltage and voltage swell. Over voltage and voltage swell. Now the term itself, it's clear, it's increase in voltage above its rated value, above normal value. Now over voltages of very short duration and high magnitude are called transient over voltages. Like you have already seen transients like this or transients like this. They are also over voltages, but they are of very short duration. So that's why they are called transient over voltages or voltage surges or voltage spikes. And we don't categorize them here in over voltages and voltage swell. We categorize them in transients. We have already seen that category. Okay. Now the over voltages with a duration between about 1 cycle and 1 minute is called voltage swell. So over voltage between 1 cycle and 1 minute duration, it's called voltage swell. And if over voltage is more than 1 minute, I mean if it is a long duration over voltage, then long duration over voltage is called over voltage itself. Okay. Now there is increase in the voltage, it's more than 10%. The voltage when there is voltage over voltage or voltage swell, the magnitude increases above the rated value by 10%, I mean greater than 10% and less than 80%. Okay. I mean if your voltage is say V, it may become 1.1 times V, that's increase in 10%, or it may go as high as 1.8 V, increase in 80%. Okay. So if there is an increase in voltage, voltage goes up to increases by 10% or greater than 10% but less than 80%, then it's called voltage swell. And voltage swell looks like this. You can see this is normal voltage and then there is swell in the voltage because of certain reason, and then voltage comes back to normal value. So this is swell, increase in the voltage. Now the question is, what are the causes of these over voltages? And over voltage can result in a single line to ground fault. Single line to ground fault. See, in a weak system where the line is not properly grounded, transformer is not properly grounded, I mean distribution transformer, as line to ground fault will raise the voltage of other two phases. The line which is grounded, for example, let us suppose this line is grounded, iski voltage kam ho jayegi, but other two lines inki voltage बढ़ जाएगी. You might have studied it in your power systems course that a single line to ground fault raises the voltage of other phases. So when the voltage of this phase and this phase is risen, when it rises, it's nothing but voltage swell. It results in increase in the voltage. Other cause is lightning stroke or strokes. Okay. Other cause is capacitor bank energizing. You are energizing capacitor bank and that results in voltage swell or over voltage. And then there is another cause. Another cause may be, there may be a resonance between transformer magnetizing reactance. Xm is the magnetizing reactance of transformer, and capacitance of the capacitor bank or capacitance of the underground cables. Suppose you are using underground cables. Underground cables have strong capacitance. This capacitance of underground cables, or this may be capacitance of power factor correction capacitors, this may fall in resonance with transformer magnetizing reactance, and that will give rise to a phenomenon which is called ferro resonance. And this ferro resonance gives rise to over voltages, that is voltage swells. And these over voltages, because of ferro resonance, they last for a longer period, and they may cause severe damage to power system equipment. So that was about over voltage. So therefore, the three types of power quality problems after transients are interruption, voltage sag, and voltage swell. So I can sum up with the help of waveforms all these, with the help of a single waveform, all these types of power quality problems. This is interruption. This is voltage sag. And this is voltage swell. And then it comes back to normal values. So in one waveform, I can show you all the three types of power quality problems. This is interruption. This is voltage sag. And this is voltage swell. Interruption means loss of voltage. It may become 0 or less than 1% or 10% of declared value. This is sag, drop in the voltage. You can see drop in the voltage. And this is swell, increase in the voltage. So this voltage swell is also not good for the system, because this voltage swell may result in insulation breakdown and damage to the equipments. So I can summarize them with the help of these charts or graphs like this. Along x-axis I have event duration, and along y-axis I have event magnitude. All the events which I have discussed with you, whether it's a transient, whether it's an interruption, whether it's a voltage sag, or whether it's a voltage swell, we can show that in a single diagram like this. Single diagram like this. So this is 0. This is 0.5. I'm sorry, I have to change the pen. This is 0.5 second, 0.5 cycle. This is 3 seconds. This is 1 minute. MIN means minute. So this is 10% of event magnitude. This is 90% of event magnitude, 90%. So we can categorize it like this. And this is 110% of event magnitude. Let me first of all draw, then I will explain. This is normal operating voltage. Normal operating voltage. Normal operating voltage is between 90% and 110%. Okay. Then you have this. This is 1 minute. This is 3 minutes here. 3 minutes. This is short interruption. Short interruption. If you remember just few moments back when we were discussing about interruptions, I told you that according to IEC, or according to this standard, EN 50160 standard, which is IEC standard. And a short interruption has a duration of 0.5 cycle to 3 minutes. I mean, it can last up to 3 minutes. So this, and in the short interruption, the magnitude may go less than, sorry, this is not 10%, this is 1%, less than 1%. The magnitude may go up to 1% or less than 1% of the magnitude. Magnitude of the voltage at supply terminals goes to as low as less than 1%. So if the interruption is for a duration greater than 3 minutes, then it is long interruption. So this is long interruption. So this is transient. This is here you can show the transients, because transients have a very high amplitude and transients are of very short duration, right? And now this is voltage dip. IEC does not call it voltage sag. IEC calls it voltage dip. Voltage dip. Just few moments back, I told you that voltage dip has a duration up to 1 minute. And if the duration is more than 1 minute, then it is under voltage. Okay? And this is temporary over voltage. Temporary over voltage, and this is over voltage. So this is all types of, see, transients are shown in this diagram. Short interruption, long interruption in the same diagram. Voltage dip and under voltage in the same diagram. Temporary over voltage and over voltage in the same diagram we have shown. Temporary over voltage means voltage swell. Voltage swell and over voltage in the same diagram. But this is as per standard EN 50160 IEC standard. What about IEEE standard? If you use IEEE standard, according to IEEE standard, then you will have this type of diagram. Let us use IEEE standard. This standard 1159 1995. 1995 means that this standard was published in the year 1995. IEEE standard 1159-1995. So as usual, x-axis is event duration. All the events we will show in this diagram, and y-axis is event magnitude or event amplitude. Event magnitude, y-axis. Now this is 0, this is 0.5 cycle, half cycle as usual. Now this is 10% of rated value. This is 90% of rated value. This is 110% of rated value. Now this is, let me first of all show normal operating voltage. If the voltage is between 90% and 110%, it is normal operating voltage. Normal operating voltage. Okay. Then what is this? If voltage is very high, but for very short duration, these are nothing but transients. Impulsive transients and oscillatory transients. Now this is 3 seconds. This is 1 minute, and so on. As you already know, if the voltage falls below 10%, but its duration is from 0.5 cycle to 3 seconds. Just few moments back, we have defined it as momentary interruption. Momentary interruption. Just few moments back. If the duration is from 3 seconds to 1 minute, it's called temporary interruption. Temporary interruption. And if the duration is greater than 1 minute, it's called sustained interruption. So this is summary of everything. I mean, you can remember these events with the help of this diagram also. Then this is voltage sag. As you know, voltage sag is decrease in the voltage from between 10% and 90%. Just few moments back we have defined it. If the voltage drops up to 90% or less than 90%, but up to 10%, not less than 10%. Less than 10% means interruption. So if the voltage drops, dips, and it is between 90% and 10% of declared value or rated value, it is voltage sag. And if this voltage sag is there for 1 minute, it's called voltage sag. And if this sag or if this dip in the voltage is for a duration greater than 1 minute, then it is called under voltage. Under voltage. So short duration voltage under voltage is called voltage sag, and long duration under voltage is called under voltage. If the sag or dip in the voltage is up to 1 minute, it is voltage sag. If the duration is greater than 1 minute, it's under voltage. Similarly, if the increase in voltage is above 110%, I have already told you, if the voltage goes up to 110% or slightly more than 110%, then up to 1 minute, it's called voltage swell, short duration increase in voltage. And if the increase in voltage is for a longer period, greater than 1 minute, then it's called over voltage. So all types of events are summarized in this diagram. Interruptions, first of all, transients, then interruptions, all three types of interruptions as defined by IEEE standard 1159, that is momentary interruption, whose duration is 0.5 cycle to 3 seconds, temporary interruption, whose duration is 3 seconds to 1 minute, and sustained interruption, whose duration is greater than 1 minute. Then take under voltages at voltage sag. Voltage sag is the decrease in the voltage, dip in the voltage between 90, and it is between 90% and 10% of declared value. If it is for short duration up to 1 minute, then it is called voltage sag. And if it is of a longer duration, greater than 1 minute, it's called under voltage. Similarly, if the voltage goes as high as 110% or greater than 110%, then it's called voltage swell if the duration is up to 1 minute, and if the duration is greater than 1 minute, it's called over voltage. So that is all about various types of power quality problems which come under this category, that is under the category of events. So what we have learned in this category, what we have learned in these events. Now we have learned that these events are the phenomena which only occur once in a while, and various classes or various types of events are transients, interruptions, voltage sag, and voltage swell. Transients are of two types, impulsive transit and oscillatory transits. We have already studied them. Then interruptions or voltage interruptions or supply interruptions also we have studied. According to IEC, interruptions are of two types, short interruptions and long interruptions. Short interruption is an interruption whose duration is up to 3 minutes, and long interruption has a duration greater than 3 minutes. And according to IEEE, interruptions are of three types: momentary interruption, temporary interruption, and sustained interruption. Momentary interruption has a duration from 0.5 cycle to 3 seconds. Temporary interruption has a duration from 3 seconds to 1 minute. And sustained interruption has a duration greater than 1 minute. Then we studied about under voltage and voltage sags. And finally, over voltage and voltage swells. Okay. Now, summarizing various types of power quality problems and their effects that we have been studying over last 4 to 5 lectures. We had broadly classified all types of power quality problems into two categories. One is voltage and current variations, and second is events. Then voltage and current variations was further divided into different 8 categories. Number 1, voltage magnitude variation, then frequency variation, then voltage fluctuation, then voltage flicker, then current magnitude variation, current phase variation, voltage and current imbalance or three-phase unbalance, and voltage distortions. We have studied that over last 2 to 3 lectures, and in today's lecture we studied about second type of power quality problem, that is events, and we classified events into transients, interruptions, voltage sags or under voltages, and voltage swell or over voltage. And all these types of power quality problems are detrimental for operation of various equipments, especially sensitive equipments, whether they are for commercial purposes, for hospitals, for industries. They result in, they may result in damage of the equipment, they may result in tripping of the processes, interruption of the processes, loss of revenue, and so on. Therefore, we have to provide mitigation of all these power quality problems. Our future lectures will be since we have already studied various types of power quality problems. Now, that means as a doctor, I know what is the disease. I have studied all types of diseases. Now, I have to give the prescription to the patient, and I have to prescribe the medicine for, fighting this disease, for curing the disease. I have found the disease in my distribution system. That's these power quality problems. Now I have to provide solution to these power quality problems. Our all future lectures, inshallah, will be focused on providing solutions to these power quality problems, because we have already understood that if these power quality problems are left unattended, they will result in problems in the system. They result in tripping of the processes, loss of revenue, damage to the equipments, and all other types of technical and financial problems in the system. So we have to address those problems. So our future lectures will be around addressing these power quality problems. But before we end today's lecture, let me give you some idea about power quality standards. Power quality standards. I have already been discussing these power quality standards with you, like IEEE standard 1159 1992, IEC standard 61000-4-15, similarly other IEC standards, and EN 50160. So if you go through the literature, and you will see that different types of these standards have been published by these IEEE or IEC to quantify different types of power quality problems, like transients, voltage sag, voltage swell, interruptions, voltage flicker, harmonics. They are very well quantified by various types of these power quality standards, like IEEE standard 1159. This is not 1992, this is 1995. Similarly, IEC, there is another standard, IEC 61000-2-1. This takes care of transients. Okay, this gives the definition of transient and the limits. It quantifies those transients. Similarly, there is IEC 61009-2-1. It is regarding voltage sags and voltage swells and interruptions. And regarding the harmonics, there are various standards like IEC 61000-2-1 1990, and a very famous IEEE standard is IEEE standard 519 1992. According to IEEE standard 519 1992, the harmonic content or the total harmonic distortion in voltages and currents should be less than 5%. If it is greater than 5%, then the quality of waveform is considered a bad quality, and then you have to take the mitigation steps. That was about something brief about power quality standards, and then power quality monitoring. Now the question is, when you have to provide solution to these power quality problems, before providing the solution to these power quality problems, you have to monitor them. So you need certain equipments, like you must know if a voltage waveform is distorted like this. Say you have this type of voltage waveform, and you want to convert this voltage waveform into sinusoidal voltage waveform. You must know what is the total harmonic content or level of pollution in this voltage waveform. And that level of pollution is given by one parameter that is called total harmonic distortion. This total harmonic distortion is VH square under root of VH square by V1. I mean, it's the summation of these harmonics, say V3 square plus V5 square plus V7 square, so on, divided by fundamental component of the voltage. So this gives, the higher the harmonic or higher the pollution in the waveform, higher the harmonic content in the waveform, more will be the THD of the current, total harmonic distortion of the current. So this THD gives us an idea about how polluted our voltage or current waveform is. Higher the THD of current or voltage, that means the very bad or poorer the quality of waveform is. More pollution is there in the waveform. But once you know the pollution, you must know what is the contribution. So let us say, for example, THD is 49%. So say THD of this waveform is 49%. And you want to compensate this voltage, and with the help of filter, you want to convert this distorted voltage waveform into a pure sinusoidal voltage waveform. So for designing the filter, you must know the contribution of all harmonics, I mean predominant harmonics, like what is the contribution of third harmonic, what is the contribution of fifth harmonic. I mean contribution means what is the percentage of third harmonic available in this waveform. What is the fifth harmonic? What is the contribution or magnitude of seventh harmonic? What is the magnitude of ninth harmonic, 11th harmonic? And you don't need to bother about higher order harmonics, because higher order harmonics have very small amplitude and they are not a cause of concern. For filtering them out, you need a simple high frequency, high pass filter that will take care. But the cause of concern is low order harmonics, third, fifth, seventh, ninth, and 11th. So unless you know what is the amplitude of third harmonic in a particular waveform, fifth harmonic, seventh or ninth harmonic, how can you design the filter? Or how can you design the compensation scheme? You cannot. Similarly, if there is a dip in the voltage, I mean this is voltage and there is a voltage sag. Now you want to compensate for these voltage sags. You want to design a strategy which will take care of these voltage sags. You must have some equipment which will measure the level of voltage sag, I mean how much dip in the voltage has been there. Similarly, voltage swell, voltage flicker. So all these parameters, all these types of power quality problems which we have been discussing over last few classes, last few lectures, you need some equipment for monitoring these power quality problems. And these equipments are luckily available nowadays in the market. They are called harmonic analyzers or spectrum analyzers. Harmonic or spectrum analyzers. And these harmonic or spectrum analyzers, these equipments, since they are available in the market, they work on the basis of FFT, fast Fourier transform, FFT. What they do? They take the online, this voltage waveform. Suppose the voltage waveform is like this. So in the real time, the data of this voltage waveform is fed, and fast Fourier transform technique, FFT technique, is applied. And using this FFT technique, THD of this voltage is calculated. And if there are sags, swells, flickers, all other parameters is also calculated in real time. So for that purpose, they need very fast digital signal processors, DSPs, which will implement these FFT algorithms, and they will calculate THD of the waveform. They will find what is the voltage sag, what is the voltage swell, what is the voltage flicker, and so on. And all this has to be done online. And let me tell you, I am very pleased to share with you that in our power electronics laboratory, in electrical engineering department of NIT Srinagar, we have purchased various power quality monitoring equipments. We have there about 3 to 4 power quality monitoring equipments. Power quality, we call them power quality analyzers. And they are from Fluke. Fluke is a British company. They manufacture high standard power quality analyzers. We have 3-phase power quality analyzers available in the lab, and we have some single phase power quality analyzers also available in power electronics laboratory. Those of you who want to work towards their projects or dissertations later on in the second year, or in the second year, they want to take their projects, they want to work on power quality problems, they will be allowed to use these Fluke power quality analyzers, because for addressing the power quality problems, they need power quality monitoring. And these high resolution, high definition power quality analyzers from Fluke are already available in our labs, and we have all other type of facilities available in our lab, power electronics lab. And those of you who are interested in doing their projects and dissertations in this area, in the area of power quality, they will definitely use these power quality analyzers. So these power quality analyzers, they take the data in real time, analyze them. They will give you, if there is a voltage sag, they will exactly give you the time, the duration of voltage sag, and the sag amplitude also. Similarly, swell amplitude, flicker, harmonics, THD of the voltage, THD of the current, everything can be monitored there. That is about power quality monitoring. So therefore, for designing the compensation techniques, power quality monitoring is very, very important. And for power quality monitoring, you need these harmonic or spectrum analyzers or power quality analyzers, which are based on the FFT algorithms, and they are implemented using high-speed digital signal processors, DSPs. So with this, I will end my today's lecture. And at the end of this lecture, today's lecture, we have come to an end of discussions on various types of power quality problems and their impact on the end users and end user equipment. Inshallah, from our next lecture onwards, we'll start now discussing about solutions to these power quality problems. We now know various types of power quality problems. Once we know and understand various types of power quality problems, we have to provide solution to these power quality problems. With this, I will end my today's lecture. All the best to all of you. I advise all of you to please go through today's lecture, and in case of any queries, please feel free to ask me. Thank you.